So the jet stream snapped. That's the phrase I've seen about 40 times this year, and I want to gently point out that it can't. The jet stream is a river of air. Rivers don't snap. Nothing up there broke, came apart or failed. What it did was wander off its usual line, and then, at various points, stop moving altogether. And honestly, that's a better story than the headline version. Because the headline version is over in one sentence and the real one isn't. This is going to be a long, meandering one. 8 things worth knowing about the jet stream, roughly equal in size in no particular order, none of them building towards a big reveal at the end. There isn't a big reveal at the end. If you drop off somewhere in the middle, you haven't missed the good bit, because the good bits are scattered all the way through. We'll do a Japanese meteorologist and his balloons, a genuinely strange weapons program, an aeroplane going faster than sound without breaking the sound barrier, and an argument between scientists that's been running for 14 years. Subscribe if you fancy it. Otherwise, let's get on with it. Let's start with a man standing in a field in Japan letting go of a balloon. His name was Wasaburo Oishi, born in 1874 in Tosu, down in Saga Prefecture, and by the early 1920s he was running Japan's first proper upper-air observatory at a place called Tateno, northeast of Tokyo. Upper-air observatory is a grand name for what was at the time a fairly modest operation. You fill a small balloon with hydrogen, you let it go, and then you watch it through a theodolite, basically a very precise telescope on a swivel, and you write down where it goes and how fast it gets there. Do that enough times and you can build a picture of the wind at heights no human being had ever meaningfully visited. Oishi did that 1,088 times between March 1923 and February 1925. That's the bit that gets me, not the discovery, the sheer grinding repetition of it. Nearly 1,300 launches over 2 years, in all weathers, mostly by hand, and every single one producing a few numbers in a notebook. And what those numbers showed, once he'd stacked them up and sorted them by season, was that in winter, about 10 kilometres above his head, there was wind moving west to east at speeds that made no sense. Not gusts, not a freak day, a permanent feature. Something that was just there, every winter, tearing across the sky above Japan while people on the ground went about their business in ordinary weather. He wrote it up. The winter profile from that data is the first known evidence of the persistent strong westerlies over Japan that the world would eventually call the jet stream. He'd found it. Comprehensively, rigorously, first, with more data behind it than anybody else would have for decades, and then he published it in Esperanto. I need to sit with that for a second, because the first time I read it, I assumed I'd misunderstood. He didn't publish a summary in Esperanto. He didn't do an Esperanto edition alongside a Japanese one and an English one. The first official report from the Aerological Observatory at Tateno, written in 1926, is in Esperanto, and then so is the next one, and the next. 19 reports between 1926 and 1944. 1,246 pages. All of it in a language invented in the 1880s by a Polish eye doctor who thought the world would get on better if everyone shared a neutral second tongue. Now, before we all pile on, this wasn't random. Oishi wasn't eccentric in the sense of being unmoored. He was the second board president of the Japanese Esperanto Institute from 1930 to 1945. He ran the thing. He genuinely, sincerely believed that Esperanto was how science was going to talk to itself across borders, and he wasn't alone in that at the time. It was a real movement with real momentum. The idea was that if you published in English, you were doing politics, and if you published in Esperanto, you were doing science, cleanly, for everybody. It's a lovely idea. It was also, as a strategy for telling the world's meteorologists that there was a river of wind above their heads, an absolute catastrophe. Because the world's meteorologists were not learning Esperanto. They were busy. And so Oishi's work sat there, correct, thorough, ignored, in a language almost nobody in his field could read, for the better part of 2 decades. Here's a fun detail that makes it worse. It's not that nobody could have found it. The reports existed. They were sent out. They were in libraries. Anyone who'd cracked one open and had the patience to work through it, Esperanto is deliberately easy, that was the whole point of it, would have had the answer sitting right there in a table. The information wasn't hidden. It was just wearing a coat nobody recognized. So the jet stream got discovered again. In 1939, a German meteorologist called Heinrich Seilkopf working at the Meteorological Observatory in Hamburg, independently found the same thing, and Zelkow named it. The German word he used is the ancestor of what we say today, jet stream, from Strahlströmung. So the name we've all used our entire lives comes from the man who found it second, in a different language, 13 years later, on the other side of the world from the man who actually found it. I wish he doesn't even get the word. And then the war happened, and the jet stream stopped being an academic curiosity and started being a problem people were dying over. When American B-29s began flying high-altitude bombing runs over Japan, they went in at around 30,000 feet, which was the whole point of the aircraft. Get above the flak, above the fighters, drop from a height nobody could reach you at. And what they found up there was a wind that made the entire exercise close to pointless. Crews would come in on a bomb run and discover that their ground speed was nothing like their airspeed. Bombs missed. Not by a bit, by a lot, because a bomb released into a 200-mile-an-hour crosswind at 6 miles up is not going where the bomb site thinks it's going. Fuel calculations that had worked everywhere else in the world stopped working. Aircraft heading into it were essentially hovering. They had walked straight into Oishi's wind, and nobody had told them it was there, because the only man who'd properly documented it had documented it in Esperanto. That's the version of the story that gets told, and it's roughly right, though I'd add a caveat. Aircraft encounters during the war are what really kicked off serious post-war research into the jet stream, and the scientist who did that research eventually went back and found Oishi's work and gave him credit. So it's not that he was erased, he was just very, very late to be read. The recognition arrived in the form of historians going through the archives at the Aerological Observatory and going, oh, he had all of this. In 1926, Oishi died in 1950. He'd been given the Order of the Sacred Treasure, which is one of Japan's oldest honours, so it's not like he lived in obscurity. But he never got the thing where the world's atmospheric scientists said his name in the same breath as the discovery. That took another 50-odd years, and a paper in the Bulletin of the American Meteorological Society, published in 2003, which went back through the memoirs and the archival records and reconstructed how a schoolteacher's son from Saga ended up running Japan's first upper-air observatory and finding one of the largest features of the atmosphere before anyone else. 77 years after the report. That's the gap. I find this one of the quietly sad stories in science, and I also, find it a bit funny, in the way that things are funny when they're too specific to be tragic in a clean way. If he'd been suppressed, or robbed, or disbelieved, it'd be a different sort of story. He wasn't any of those. He was just so committed to a bet about how humanity ought to communicate that he took the biggest thing he ever found and put it somewhere nobody was looking. There's a version of this where I'd tell you the lesson is about publishing in English, and I'm not going to do that, because I don't actually think that's the lesson. The lesson, if there is one, is that being right isn't a delivery mechanism. Being right doesn't move on its own. Somebody has to be able to read it, and somebody has to be looking, and if either of those fails, then correct information just sits there being correct for 20 years while the rest of the world reinvents it at considerable expense. One more thing about the balloons before we move on, because I think it's easy to picture this as a man with a helium party balloon and lose the scale of what he was doing. Pilot balloon observation, which is what this was called, is a proper craft. You inflate to a known volume so you know your rate of ascent. You release, you track it through the theodolite. You take a bearing and an elevation angle at fixed intervals, every minute usually, and then you do trigonometry to work out where the balloon actually is in 3 dimensions at each of those moments. Difference between consecutive positions gives you the wind at that height. It's not complicated maths, but it is relentless maths, and you're doing it by hand, and you're doing it every clear day for 2 years, and any one of them can be ruined by cloud, because the second you lose sight of the balloon, the observation's dead, which means the real number of launches was higher than the number of usable ones. Every clear winter day at Tateno, somebody was out there, and the reward for all of it was a table of seasonal mean wind profiles that a handful of people read, and the reports themselves have a title, which I only found out recently, and which I now think about more than is reasonable. Rapporto de Aerologia Observatorio de Tateno, Report of the Aerological Observatory of Tateno. That's Esperanto, and you can more or less read it without knowing a word of the language, which was rather the entire pitch. Zamenhof built the thing in the 1880s out of borrowed European roots and a grammar with no exceptions in it, precisely so that a stranger could pick up a page and get about 70% of it on sight, which is the part that turns this from unlucky into properly maddening. It wasn't a code. It wasn't obscure in the way that a manuscript in a lost script is obscure. Any European meteorologist who'd opened one of those reports would have looked at Rapporto de Aerologia Observatorio and gone, right, well, that's obviously what that says, and then found tables. Tables are language neutral. The numbers are just numbers. Height, direction, speed, season. The wind was in there in a form that didn't need translating at all, and it sat there for years because the cover put people off. There's a second half to this that I think gets skipped, and it's about who eventually did the work of turning a curiosity into a science. Because finding the jet and understanding it are two different jobs, and Oishi only ever did the first one. He measured it. He couldn't tell you why it was there. That took Rossby, Carl Gustaf Rossby, a Swede who ended up in America and who we're going to run into again, and his students, working through the 1930s and then very intensively after the war, once those B-29 crews had come home and made the question urgent. Rossby's the one who built the theory. He's also, and this matters more than it sounds, the one who built the school. He trained a generation of American meteorologists more or less single-handedly, and it was that generation who took the jet stream from a strange thing pilots complained about to a thing you could put on a chart and reason with. So the discovery has 3 men in it, none of whom worked together, none of whom shared a language, spread across about 25 years and 3 continents. Oishi measured it and told nobody who could hear. Seilkopf found it again and named it. Rossby explained it. And of the 3, the one with the least claim to the credit is the one whose word we all use. Anyway, that's where this whole thing starts. A man, a field, a theodolite, and a filing decision that cost the world about 15 years. We'll come back to Oishi right at the end because there's a nice symmetry in what happened to his data eventually, and I'd rather leave it there than use it up now. The balloons carry on after him though, and the numbers carry on after him, and one of the places they ended up is a thing called Fugo. So let's talk about that for a bit. Picture the object itself first because it's genuinely beautiful, and that's an uncomfortable thing to say about it. It's a sphere, roughly 10 meters across when inflated. It's made of washi, mulberry paper, laminated in layers with konjaku paste, which is a glue made from devil's tongue root, essentially a starchy potato. The paper is stuck together in 3 or 4 plies, painted and lacquered. Some of the later ones were silk. Underneath hangs a ring of sandbags on individual releases, a barometric altimeter, a clock mechanism, and the payload. It's filled with hydrogen. It weighs about 200 kilos all in, and it was designed to cross the Pacific Ocean on its own, unpiloted, unguided, with nobody watching it, for somewhere between 2 and 3 days. The Japanese called it Fusen Bakudan, balloon bomb. The program was Fugo. Here's how it worked, and I think this is the part that deserves a bit of admiration, even given what it was for. The problem with a free-floating balloon is the altitude. In sunlight, the hydrogen warms and expands and the thing climbs. If it climbs too far, the gas bursts the envelope. At night, it cools and contracts and the balloon sinks. If it sinks too far, it hits the ocean. So over a 3-day crossing, you'd naturally oscillate yourself to death within about 1 cycle. The fix was an automatic system with no electronics in it worth mentioning. An aneroid barometer sensed altitude. Drop below about 30,000 feet, and a circuit fired a small charge that cut loose one of the sandbags. Light a balloon, back up it goes, climb above about 38,000, and a valve vented hydrogen off the top. Down it comes. So the balloon sawtoothed its way across the ocean, shedding a bag of sand each night and burping out gas each day, staying inside a band roughly 7 miles up. Which is, and this is the entire point, exactly where the wind we've been talking about lives. When the last sandbag was gone, the same mechanism dropped the bombs and then, on some designs, set fire to the balloon itself. Now, how did anyone know how long that journey took, or how much sand to bring, they asked. After the Doolittle raid in 1942 shook the Japanese leadership by putting American bombers over the home islands, the 9th Military Technical Research Institute was told to come up with a way of hitting back at a continent they had no way of reaching. The weapons people could build the balloon. What they couldn't do was tell you whether it would arrive. So they went to Hidetoshi Arakawa at the Central Meteorological Observatory in Tokyo, and Arakawa drew on the work of the man we just spent 20 minutes on. Oishi's wind. The wind he'd documented, he'd said 8 times, and published where nobody could read it. It turned out somebody could read it, his own colleagues, in his own country, who had every reason to know exactly what he'd found. The data went into a weapon. I don't think there's a clean thing to say about that. He didn't build it, and there's no suggestion he wanted it built, but it is the first practical use anyone put the Jetstream to, and it's this. They launched about 9,000 of them. That's the number that gets cited, and it's the one I'd trust, at least 9,000, from 3 coastal sites on Honshu, over roughly 8 months starting in late 1944 and running into the spring of 1945. The launches were done at night and in winter, deliberately, because winter is when the wind is fastest and the crossing is quickest. Of that total, about 300 are known to have made landfall in North America. That's the figure from reports of pieces found, which means it's a floor, not a ceiling. Plenty came down in forests and lakes and were simply never seen. They turned up in Oregon, Washington, California, Alaska, Montana, Wyoming, and across into Canada as far as Saskatchewan. One got as far east as Michigan. One came down near Detroit. A few landed in Mexico. The intent was to start forest fires across the American West. In terms of that objective, it did essentially nothing. Winter and early spring is the wettest part of the year in the Pacific Northwest, which is a detail the planners either didn't have or didn't wait properly, and a firebomb landing in a soaking wet Douglas fir forest in February is not a forest fire, it's litter. But on the 5th of May 1945, near Bly in Oregon, a woman called Elsie Mitchell drove out to a spot on Gearhart Mountain with 5 children from her husband's Sunday school class for a picnic. Her husband, Archie, was parking the car. The group found something in the trees and went over to look at it. It went off. All 6 of them died. Elsie Mitchell was 26 and pregnant. The children were between 11 and 13. They are the only people killed by enemy action on the American mainland during the Second World War. 6 people on a picnic in a forest from a paper balloon that had crossed an ocean on a wind a Japanese meteorologist had measured 20 years earlier and told the world about in a language it didn't speak. Archie Mitchell survived, because he was still at the car. I said in the opening this was going to be a relaxed one, and I'm going to keep my word on that, so I'm not going to sit in this. But I'm also not going to skip past it lightly, because the whole reason the story's told is that it's the one moment where all of this stopped being abstract for anyone. Here's the part that connects back to the press. The American government had known about the balloons since late 1944. They'd found them. They knew roughly what they were and had a fair idea where they'd come from. Geologists analysed the sand in the ballast bags and worked out which beaches on Honshu it had come from, which is a wonderful bit of detective work and also a fairly grim one, and the decision they made was to say nothing at all, a total press blackout. Newspapers were asked and agreed not to print a word. The logic was that Japan had no way of knowing whether any of the balloons were arriving. They were firing them into the void. If American papers ran stories saying balloon lands in Oregon, then Japan would know the range was right and would scale the program up. If the papers said nothing, the whole thing would look like a failure, and it worked. Japanese intelligence found essentially one mention, from a report of something coming down in Wyoming, and otherwise had nothing. The program was shut down in April 1945, partly for want of hydrogen, and partly because as far as anyone in Tokyo could tell it was achieving nothing whatsoever. The blackout worked, is the thing. It ended the program. It also meant that on the 5th of May, a group of people in a forest in Oregon had no idea that the object in the trees was anything other than an object in the trees, because nobody had been allowed to tell them. The blackout lifted immediately afterwards. Warnings went out, and by then there was nothing left to warn about, because the launches had already stopped a fortnight before. That is a genuinely horrible piece of timing, and I don't think anybody involved made an obviously wrong call at any single step. Which is somehow worse. Right, let me lift this, because there's a strange coda that I like. Those balloons are still out there. Not many, but they haven't all been found. One turned up in British Columbia in 2014. Forest workers came across the remains of one, and a bomb disposal team blew it up in place because a 70-year-old incendiary is still an incendiary. There have been finds in Alaska, in Oregon, scattered across the decades since. Every so often somebody in the Pacific Northwest walks into the woods and comes out having met the Second World War. And there's one detail I love purely as an engineering fact. The paper. That washi envelope was made in workshops and schools all over Japan, in sections, by hand, largely by teenage girls, who glued the plies together and were never told what they were making. Some of them worked in theatres and sumo halls, because those were the only buildings with floors big enough to lay the panels out. They were assembling the panels of a weapon designed to cross the Pacific, and they thought they were doing paperwork for the war effort, which, technically, they were. And the sand. I mentioned it in passing, and it deserves more than that, because it's one of the great pieces of forensic work of the war, and hardly anybody's heard of it. When the Americans started recovering these things, they had a straightforward problem. They had no idea where they were coming from. The obvious theories were all wrong and all frightening. Submarines launching them off the coast, prisoner of war camps, landing parties. Nobody's first instinct was that they'd come from Japan, because Japan is 5,000 miles away, and that's not a distance you cross in a paper bag. So they took the ballast, the sandbags, and they gave the sand to geologists who did the thing geologists do, which is look at grains under a microscope and identify what they're made of and what shape they are, and what microscopic fossils are mixed in with them. Sand has a fingerprint. It comes from somewhere, and the somewhere is written into it. They ruled out American beaches, they ruled out the Pacific Islands, and then they matched it to specific beaches on Honshu, which is exactly where the launch sites were. They worked out where the weapon was coming from by looking at the dirt it carried. That is an absurdly good piece of science, and it was done by people who had no reason to think it would work. There's one more thing I want to say about the girls in the workshops, because I glossed it, and I shouldn't have. Those panels had to be enormous, and they had to be flawless, because a pinhole in a hydrogen envelope at 30,000 feet is a dead balloon. So the work was slow, precise, and done on hands and knees on the floor, brushing konjaku paste between sheets of mulberry paper and smoothing out every bubble. It was done in schools and in workshops, and, because those were the only interiors in the country with floor space to lay out a 10-metre sphere's worth of panels, in theatres and sumo halls. Picture that. A sumo arena, a national sporting cathedral, with the ring gone and the floor covered in paper, and a few hundred schoolgirls on their knees, gluing. And the konjaku paste was edible. It's food. It's made from a root that people eat. Japan was on rations, and there was a paste made of foodstuff being brushed onto paper by hungry teenagers all day, and the accounts that survive make it fairly clear that some of it got eaten, which was a punishable offence, and which is possibly the most human detail in this entire story. Most of them had no idea what they were making. They were told it was war work. It was. Anyway, 9,000 paper balloons and one wind. It's the only time in history anyone has tried to use the jet stream as a delivery system, and it half worked in the worst possible way at the smallest possible scale. Which does raise the question of what this thing actually is, given that we've now spent a while talking about people who found it, named it, flew into it, and fired weapons down it, and I haven't yet told you what it's made of, so let's do that. Right. The thing itself. I've deliberately not led with this because every explainer on Earth opens with the diagram, and I think it makes the jet stream sound like homework. It isn't homework. It's the most interesting object in the sky, and you can't see it, which is a rare combination. Start here. 6 to 8 miles above your head, call it 30 to 40,000 feet, cruising altitude, the height of the little screen on the seatback. There is a band of wind moving from west to east. It's a few hundred miles wide, a couple of miles deep, and it goes all the way round the planet. It's doing that right now. It was doing it while you were asleep last night, and it'll be doing it next Thursday. Where does it come from? It comes from a temperature difference, and that's the whole thing. That's genuinely the whole mechanism, and everything else in this video is a consequence of it. Cold air is denser than warm air. So where you've got very cold air sitting next to much warmer air, and the biggest example of that on the planet is the boundary between polar air and the air from further south, you get a steep difference in pressure between the two, and that difference gets more pronounced the higher you go. Air moves from high pressure to low pressure. So at altitude, along that boundary, air starts sliding sideways, hard, except it doesn't go straight. Because the planet is spinning. This is the Coriolis effect, and I'm going to describe it the way that finally made it land for me, which is, the Earth is turning underneath the air. Anything moving over the surface of a rotating sphere gets deflected, right in the northern hemisphere, left in the southern. So air that starts off trying to move from the warm side to the cold side gets turned, and ends up not crossing the boundary at all but running along it. West to east. That's the jet stream. It's not a wind that goes somewhere. It's a wind that's permanently trying to go north and being bent sideways, by the rotation of the planet until it just runs a lap instead. Which is why I'd push back a bit on the way it's usually described. You'll hear that the jet stream pushes weather across the Atlantic like a conveyor belt or a hose pipe. That's not wrong exactly, but it puts the emphasis in the wrong place. The jet stream isn't primarily a thing that moves weather. It's a boundary. It's the line where cold air stops and warm air starts, made visible by the wind that line generates. The weather isn't being pushed by it, so much as the weather is the fight along it. Storms are what happens where those two air masses grind against each other. The jet marks the front line, and it steers what forms there, and if you move the line, you move where the fighting happens. That's why forecasters obsess over it. Not because it's dramatic, because it's the boundary, and everything else follows from where the boundary is. Now plural, there isn't one jet stream. In each hemisphere there are two main ones. The polar jet is the one we mean when we say the jet stream in Britain. It sits along that cold air meets warm air boundary at around 50 to 60 degrees of latitude, which is more or less directly over us, which is why the UK's weather is essentially a running commentary on what the polar jet is doing this week. It's stronger in winter, because winter is when the temperature contrast between the Arctic and the mid-latitudes is at its sharpest. Bigger contrast, bigger pressure difference, faster jet. The subtropical jet is further south, around 30 degrees, higher up, and driven by a different thing. It's about the edge of the tropical circulation rather than a polar boundary. It's generally weaker and less bothered about your weekend. But it matters, and it'll come back later on when we get to the argument, so file it. Both hemispheres have their own pair. The southern hemisphere's polar jet is actually stronger and tidier than ours, because there's less land down there to mess it about. Fewer mountains, fewer continents, more ocean. It just runs. And here's the thing I really want you to have, because it's the bit that makes the rest of this video make sense. The jet doesn't run in a straight line. It waves. These are called Rossby waves, after Carl Gustaf Rossby, a Swedish meteorologist who spent most of his career in America and who worked out the mathematics of them in the late 1930s. Rossby's one of those figures who's everywhere in this field once you start looking. He's the man who trained a generation of American meteorologists, and it was his students who did most of the post-war work on the jet after those B-29 crews came home with stories. A Rossby wave is a big, slow undulation in the flow. Think of the jet less as a laser and more as a rope laid out on the ground with slack in it. It bulges north here, dips south there, bulges north again. The wavelength is enormous. Thousands of kilometers. You typically have somewhere between 4 and 7 of these waves wrapped around the hemisphere at any given time. Why does it wave? A few reasons stacked on top of each other. Partly because the Coriolis effect isn't uniform. It's strongest at the poles and zero at the equator, and that gradient alone makes big flows want to oscillate. Partly because there are mountains in the way. The Rockies and the Tibetan Plateau are large enough to physically deflect the jet and set up a wave that then propagates around the whole planet. Partly because the boundary between land and sea puts heat in unevenly, and partly just because the atmosphere is a fluid, and fluids in motion do not travel in straight lines, ever, under any circumstances. Where the wave bulges north, you get a ridge, warm air pushed poleward, usually high pressure underneath, usually settled and dry. Where the wave dips south, you get a trough, cold air pulled down, usually low pressure, usually unsettled. So if you're sat under a ridge, you're having a nice week, and if you're sat under a trough, you're not, and the difference between those two is entirely a matter of which part of the rope you happen to be standing beneath. Those waves move. Normally they trundle eastwards, which is why weather in Britain has that characteristic quality of changing every 3 days. Ridge, trough, nice, horrible, nice, horrible. That's the waves marching past. And now, the fun fact, and it's the one that most people already have a personal relationship with without knowing it. Your flight home is shorter than your flight out. If you've ever flown to New York and back, you'll have noticed this. Out is longer, back is shorter, and it's not your imagination, and it's not the airline padding the schedule. The typical transatlantic jet is running at somewhere around 110 miles an hour, west to east. Going east, you sit in it and it carries you. Going west, you're pushing into it, and the airline has to route you around the edges of it to avoid the worst, which means you fly further as well as slower. The scheduling difference is often about an hour and a half, which means that every single day thousands of people are having their afternoon rearranged by a temperature difference between the Arctic and the tropics, and almost none of them know that's what happened. Airlines know. Flight planning software spends a considerable amount of its time doing nothing but looking for the jet and working out how to either sit in it or dodge it. The North Atlantic tracks, the organised routes across the ocean, get redrawn twice a day, every day, based on where the jet has got to. It's one of the very few pieces of weather that has an entire piece of global infrastructure organised around it in real time. A couple more things worth having, and then I'll stop. The jet migrates with the seasons. It's not fixed to a latitude. In winter, when the Arctic is properly cold, and the contrast is at its most vicious, the polar jet strengthens and slides south. In summer, as the pole warms up and the contrast softens, it weakens and drifts north. That's the underlying rhythm of a British year, and it's why our winters are stormy, and our summers are, traditionally, not. Winter, the jet's on top of us with all the energy in the world. Summer, it's up past Iceland somewhere, and we're left in the calm. Which is also, incidentally, why a British summer that goes wrong tends to go wrong in one of two very specific ways. Either the jet has failed to go north, and it sits over us all August delivering Atlantic lows, and everyone complains about the washout, or it's gone north and parked, and left high pressure sitting on us for weeks, and everyone complains about the hosepipe ban. There isn't really a third option. Every British summer anyone's ever moaned about is one of those two. The other thing is that the jet isn't uniform along its length. It's not a smooth ribbon at a constant speed. It has fast cores inside it, jet streaks, which are localized patches where the wind is dramatically quicker than the rest of the flow. They move along inside the jet, they form and dissipate, and they're doing a lot of the actual work. When you hear that the jet is running at 200 miles an hour, that's almost never the whole thing. That's a streak, somewhere inside a much broader flow that's doing considerably less, and it's not a hard-edged object either. There's no wall. The wind builds gradually towards a core and falls away gradually on either side, so where you draw the boundary of the jet stream on a chart is a matter of convention rather than physics. Usually you pick a wind speed threshold and call everything above it the jet. Which means the jet stream is, in a small but real sense, partly a decision we made about where to put a line. I like that. Most of the enormous features of the world turn out on close inspection to have slightly negotiable edges. So, a band of wind 6 to 8 miles up, made by a temperature difference, bent sideways by the rotation of the planet, waving as it goes, marking the line where cold meets warm, and quietly deciding whether you get rained on, and how long it takes you to fly to America. That's it. That's the object. Everything from here on is variations on those few facts, and I'm not going to explain the mechanism again, so if you drifted off during the Coriolis bit, genuinely, don't worry about it. The short version is, it goes round, it wobbles, and the wobbles are where the weather lives. What I do want to do next is show you what happens when you take that 110 mile an hour average, and occasionally on a good night in February, absolutely wind it up. The 8th of February 2020, a Saturday evening, British Airways Flight 112 pushes back from a gate at JFK at about 6:45 in the evening, New York time. It's a 747-400, an old aircraft even then, one of the last few BA had flying. It's a completely routine service. Passengers get on, doors close, it goes. Nobody boarding that aircraft has any reason to think it's going to be interesting. It lands at Heathrow at 4:43 the following morning, 4 hours and 56 minutes after it left. The flight normally takes 6 hours and 13. It's scheduled at 7 hours and 5 to allow for taxiing and delays. So everybody on that aeroplane got to London an hour and 38 minutes early, which is a thing that has essentially never happened to anyone in the history of aviation. And the reason is that at some point over the Atlantic, the 747 was moving at a ground speed of around 825 miles an hour. The speed of sound at sea level is about 760. Now, it did not break the sound barrier. I want to be very precise about this because it's the bit everyone gets tangled in, and it's also the bit that's genuinely interesting once it clicks. An aeroplane doesn't move through the ground. It moves through air. Everything about how it flies, the lift, the drag, the shock waves, the whole business of whether you go supersonic and rattle every window in Devon, depends entirely on how fast you're going relative to the air immediately around you. And that 747 was doing exactly what it always does relative to the air around it. About 570 miles an hour. Perfectly ordinary. Utterly subsonic. The pilots weren't doing anything special. The air was moving. The air around that aircraft was doing something like 250 miles an hour eastwards all by itself. So you add the aeroplane's normal speed through the air to the air's speed over the ground, and you get that headline number over the ground. The aircraft is behaving completely normally inside a room that is itself hurtling east. The metaphor I keep coming back to is a leaf on a river. The leaf isn't going fast, the leaf is going nowhere relative to the water it's sitting in. The river is going fast, and if you're standing on the bank you'd swear that leaf was flying. Ian Petchenik from Flight Radar 24, who tracked this stuff and who'd been watching the forecast all week, waiting for exactly this, put it better than I'm going to. He said it was like a marathon runner waking up and the weather's perfect and they're feeling great and the course is a bit downhill. They knew it was coming. They knew the jet was going to be well placed that weekend. They were sat there waiting for someone to break the record. BA's statement afterwards was very British, and I enjoy it a lot. Something to the effect of, we always prioritise safety over speed records, but our highly trained pilots made the most of the conditions to get customers back to London well ahead of time. Which is a corporate press office trying to be modest while absolutely bursting. That was the fastest subsonic transatlantic crossing by a commercial airliner. It beat the previous record, which was 5 hours and 13 minutes, set in January 2018 by a Norwegian Dreamliner going JFK to Gatwick, with a 2 mile-an-hour tailwind, doing 776 over the ground. And the thing is, these records kept falling, one after another for several years running, because everyone had worked out how to watch for it. In February 2019, the jet was clocked at 231 miles an hour, which at the time was the fastest recorded since 1957. That same period, a Virgin Atlantic Dreamliner coming into London from Los Angeles hit 801 over the ground. Then February 2024 happened, and that one's my favourite because of who noticed it. The National Weather Service office at Baltimore, Washington launched a weather balloon on the evening of the 17th. This is a completely routine thing. We'll come back to how routine later, and what came back was, and I'm going to keep this in their own register because their tweet about it is delightful. This evening's launch detected the second strongest upper-level wind recorded in local history going back to the mid-20th century. Around 34 to 35,000 feet, winds peaked around 230 knots, which is 265 miles an hour. And then, because they're meteorologists and not monsters, they added a note for anyone flying east that night. There will be quite a tailwind. There was. A United 787 going New York to Lisbon hit 835 over the ground and set what I believe is still the record, for 344 kilometers an hour on the 17th of February 2024. A Virgin flight from Washington to London got to nearly 800. A Qatar 777 heading to Doha did 8:33 and landed 50 minutes early. A BA A350 in from Las Vegas did 8:14 and got in 45 minutes early. That's 4 aircraft in about a day, all of them technically covering ground faster than sound travels, none of them going supersonic, all of them doing precisely nothing unusual. I love this stuff, and I've been trying to work out why, and I think it's this. It's the only time the jet stream is physically legible. You cannot see it. You cannot feel it. There's no sensation on board, no shudder, no noise, nothing. If you were sitting on that 747 in February 2020, you would have had absolutely no idea, right up until the captain came on and said, with what I imagine was some difficulty in keeping his voice level, that we'd be arriving in London slightly ahead of schedule. The only evidence is the clock. Now, a note of caution, because I've seen this one get a bit overcooked in coverage, and I'd rather be straight with you. You'll read that these records are proof the jet stream is speeding up because of climate change. And there's a real argument there. A stronger temperature contrast across the Atlantic does mean a stronger jet, and there's genuine research on trends in jet strength and on clear air turbulence increasing, which is a related and slightly less fun consequence of the same physics. But a single fast night isn't evidence of a trend. What actually happened in February 2024, and in February 2020, and in January 2025 when Storm Eowyn was spinning up, is that there was a big cold outbreak over North America, which made the temperature contrast enormous, which energized the jet. That's weather. That's the same mechanism that's been doing this every winter since before anybody was measuring it. The reason we know about these particular nights is partly that the jet was fast and partly that Flight Radar 24 exists, and there are people whose actual job it is to watch for it. Records get broken more often when someone's watching. Some of the trend in record transatlantic crossings is a trend in record keeping. That said, 110 is the normal, so 265 isn't a slightly brisk evening, it's more than double. There's a flip side to all this that nobody puts in the headline, which is the westbound flight. Because the jet doesn't hand out free speed, it just moves air, and if you're going the other way, London to New York, London to Los Angeles, then that same night when a 787 was doing 835 towards Lisbon, somebody else was crawling into a 200-mile-an-hour headwind, burning fuel they'd planned on having, and arriving late. Which is why westbound routes aren't straight. The North Atlantic tracks, the organised motorway lanes across the ocean, get redrawn twice a day, and the westbound ones are drawn specifically to dodge. They'll take you hundreds of miles off the direct line, usually north, up towards Greenland to get out from under the worst of it. You fly further to arrive sooner, and the eastbound tracks that same day are drawn to do the exact opposite, sitting the aircraft in the core deliberately. So on any given night, the Atlantic has two sets of lanes running in opposite directions drawn to two opposite philosophies, both dictated by the same invisible thing, and both redrawn from scratch before the next lot go. There's a lovely knock-on from this, which is that a very fast jet is good news for airlines on the whole, because eastbound saves more than westbound loses when you're routing intelligently, and a very fast jet is bad news for passengers in a different way entirely, because the shear at the edge of a strong jet, the place where 200-mile-an-hour air is sitting immediately alongside 40-mile-an-hour air, is where clear air turbulence lives. That's the kind you can't see. That isn't in a cloud. That doesn't show on the weather radar because there's nothing for the radar to bounce off. It's just a step in the wind. So the same February night that gets a Dreamliner to Lisbon 50 minutes early is a night when somebody, somewhere over the ocean, is having their drink land in their lap for no visible reason. One last thing, and it's the one that reframes the whole module for me. The reason those crossings feel remarkable is that we've got used to a world where the fastest possible commercial flight is a fixed number. Concorde retired in 2003, and since then no passenger aircraft can go faster than sound. That's just a fact of the era. And what the Jetstream does, on maybe 2 or 3 nights a year, is hand a completely ordinary 787, full of people in economy, a speed that a supersonic aircraft would recognise, for free, for nothing, because the sky happened to be moving in the right direction. Nobody paid for it. Nobody engineered it. It's a temperature difference between the pole and the tropics, doing what it's done for as long as there's been an atmosphere, and once in a while a Dreamliner falls into it and gets to Lisbon early. There's something quite nice about that. The most advanced thing we can currently do in the air is get lucky. Anyway, that's the view from altitude. Since we're on the subject of what this wind does to people, let's come back down to ground level and talk about January, which is a different sort of month entirely. Let's start with a field in Cornwall, not a dramatic field, not a field with a river through it or a village downhill of it. Just an ordinary field, in an ordinary bit of the West Country, in the 3rd week of January, and the thing about it is that it's full. Soil is a sponge. That's not a metaphor, it's more or less the technical reality. There's a pore space between the particles and water sits in it, and there's a finite amount of it. A healthy field in a normal winter takes rain, holds it, lets some drain down, lets some evaporate, and by the time the next lot arrives it's got room again. The whole system is built around gaps between the rain, so the sponge can wring itself out. Take away the gaps, and the sponge stops being a sponge. It's just a lid. And then rain that would have been completely unremarkable in October. A normal, boring, nobody mentions it band of rain has nowhere to go, so it goes sideways, downhill, into the lane, into the culvert, into somebody's kitchen. That's what most flooding actually is, and I think it's one of the least understood things in weather. People imagine floods are caused by enormous rain. Sometimes. Mostly they're caused by ordinary rain arriving at a landscape that hasn't been allowed to breathe. Which is exactly what January 2026 was. Not one monstrous storm. A queue. Northern Ireland had its wettest January in 149 years. 70% above average. The only January on record that beat it is 1877. And the record goes back to 1836, so we're talking about a series that predates the invention of the telephone. County Down and Cornwall both had their wettest January on record outright. Across the UK as a whole, 17% more rain than average, which sounds modest, and it is modest, and that's the point I want to make. 17% isn't a catastrophe on paper. It caused chaos on the ground because of how it arrived, not how much of it there was. So what was the jet doing? Two things at once, which is what makes it worth talking about. The first is that it was strong, unusually strong and driven by exactly the mechanism we went through earlier, a big temperature gradient across the Atlantic. There was cold air coming down over North America repeatedly, all month, meeting warmer air, and that contrast is fuel. Sharper contrast, faster jet. The Met Office were pretty direct about it at the time. A strong jet had repeatedly steered low-pressure systems towards the UK, bringing frequent spells of rain and wind with little opportunity for drier conditions in between. Little opportunity for drier conditions in between. That's the sponge. The second thing is the bit I find more interesting, because it's the bit the headline skipped. The jet wasn't just strong, it was in the wrong place. It was displaced south, running along a more southerly line than it usually takes in winter, and the reason it was stuck down there is that there was a blocking high sitting over northeastern Europe refusing to move out of the way. I'm not going to explain blocking properly yet. That's the next module, and it deserves its own room. But the shape of it is simple enough to hold for now. A big lump of high pressure parks itself somewhere and won't budge, and the jet, which can't go through it, has to go round. In this case, it went round the south, which meant the conveyor of Atlantic low-pressure systems, instead of tracking up over Iceland the way it often does, came in from the southwest and aimed itself directly at us. So you've got a jet that's been energized by North American cold and pinned in a southerly track by European high pressure, and the UK's sat right on the delivery line, storm after storm. Goretti, named by the Portuguese, then Ingrid, also named by Portugal, then Chandra, ours, on the 26th. Chandra's the one I want to spend a minute on because Met Irian wrote about it beautifully and there's a lovely piece of physics in it. Storms don't just exist near the jet stream, they get made by it, and the geometry matters. A jet streak, a fast core within the jet, has 4 quadrants, and 2 of them are places where air gets pulled apart at altitude. If air is diverging up there, the air below has to rise to fill the gap, and rising air at the surface means pressure drops, and pressure dropping is what a storm is. It's a bit like taking the lid off. The technical term for the specific spot is the left exit region of the jet, and it is genuinely a place where storms are manufactured. Chandra deepened rapidly to the south of Ireland on Monday the 26th, in the left exit of a strong polar front jet. And that polar front jet was strong because of a cold air outbreak over North America. So you can draw a straight causal line from a cold snap in Canada to somebody's flooded living room in County Down via a wind 6 miles up, and every step of that line is solid physics with nothing hand-wavy in it. I think that's remarkable, and I don't think we say it enough. The atmosphere is genuinely a single connected object. It's not a set of regions that occasionally interfere with each other. It's one thing. Then Chandra tracked north, and this is where Ireland's version of the story diverges nicely from ours. Met Irian's account is that the same blocking high over northern and eastern Europe was causing these systems to slow or stall to the southwest of Ireland and meander northwards. So it wasn't just that storms arrived, it's that they arrived and then couldn't leave. They'd come up from the southwest, hit the traffic and sit there feeding rainband after rainband up over the country from the south. Prolonged spells of heavy rain concentrated in the south and east, on ground that was already full. Malin Head in Donegal recorded the season's highest gust and its highest 10-minute mean wind speed on the 27th. Storm force at the top of the country while the bottom of it drowned. There's something quite nice, wrong word but I can't find a better one, about 2 national weather services on either side of the Irish Sea, both writing up the same month and both pointing at the same wind. The Met Office's framing as a strong jet delivering systems, Met Irian's framing as a displaced jet and a block causing them to stall. Those aren't competing explanations. They're the same jet, described from 2 positions on the delivery route, and both descriptions are correct. A number of UK sites broke their daily rainfall records during that month. The most notable day for it was the 26th, during Chandra. Not records that had stood since the 60s, incidentally. I've seen that claim floating about. County-level records in a series that starts in 1836. England came in 50% above average. It was the 6th wettest January on record for southern England. Scotland, oddly, was below average overall, 87% of its normal rainfall, but with a huge split inside that because eastern Scotland got 48% more than average while the north and west got less. Which tells you something about how narrow this delivery lane was. The jet was aimed. It wasn't watering the whole country, it was pointing at a specific corridor and hosing it, while a couple of 100 miles northwest of the line, it was drier than usual. And when February arrived, some communities were still doing recovery work while the forecast was already showing more rain and snow coming, and another unsettled week behind that. Small aside on the names, because it's a nice bit of trivia, and it explains something about that list. Goretti, Ingrid, Chandra. 3 storms in a month, and only one of them is ours. That's because Western Europe's storms are named by a group. The UK, Ireland and the Netherlands share a list, and there are other groups covering southwestern Europe and elsewhere, and whichever service expects the biggest impact gets to name it. So Goretti and Ingrid came from the Portuguese, and Chandra came from us, and the names on our list come from the public. For the 2025-26 season, each of the 3 services in the group put in 7 names. Met Ariane asked the Irish public to submit theirs, and got more than 10,000 suggestions from about 4,000 people, which is a genuinely lovely level of engagement for a naming exercise. The full list ran Amy, Bram, Chandra, Dave, Eddie, Fioniwala, Gerard, Hannah, Isla, Jana, Kasia, Lilith, Marty, Nico, Oscar, Patrick, Ruby, Stevie, Tadug, Violet, Wubbo. That's the Dutch getting their money's worth, and I respect it enormously. The other thing I want to flag, and then I'll move on, is what this kind of month actually costs. Not in a dramatic way, in a boring infrastructure way, which is the way that matters. Britain's built environment is calibrated, that's the word for it. Reservoirs are sized around historical rainfall patterns. Flood defences are specified against a design event pulled from decades of records. Drainage is sized for a certain intensity. Railways are engineered for a temperature corridor. None of that is guesswork. It's all careful, expensive engineering, done properly, by competent people, using the best available data. And the best available data is the past. That's the whole difficulty, and it's not a failure of anybody's. If you're designing a culvert in 1975, you look at the rainfall records and you build for the wettest plausible year, which is exactly right and completely rational, and only works for as long as the past keeps being a reasonable guide to the future. A wet January in a country designed for a slightly drier one doesn't look like a disaster movie. It looks like a lane that's under 6 inches of water for the 3rd week running, and a train that isn't coming, and a farmer who can't get onto a field, and someone in an office somewhere quietly revising a design standard for the next generation of culverts. Met Irian made a point in their write-up that I thought was fair and that got lost in the coverage. January storms are a normal part of the Irish climate. The Atlantic storm track is often at its most active then, and it's not unusual to have a strong jet stream. This isn't an alien month. It's a normal month turned up, arriving at a landscape with no spare capacity in it. Right. I mentioned blocking a couple of times back there, and kept putting it off, so now let's talk a little about that because it's got a good name and a better story behind it. The Greek letter. That's it. That's the entire naming convention. If you take the jet stream on a given day and trace it west to east across a map, and it happens to dip south, then bulge way up north, then dip south again, the line you've drawn looks like a capital omega. O. So they call it an omega block. Meteorologists, as one of them cheerfully admitted this year, are not the most creative when it comes to naming things, and I mean that with affection. It's a field where the naming conventions are almost aggressively literal. A cold front is a front where the cold is, a warm sector is the warm bit, a heat dome is a dome of heat. And then occasionally somebody looks at a squiggle on a chart and goes, that's an omega, and it sticks for 80 years. Here's what's actually happening under the letter. A big area of high pressure sets up somewhere and crucially stops moving. Normally these things drift east with everything else. That's the whole rhythm of mid-latitude weather, systems parading past. A block doesn't parade, it anchors, and the jet, which cannot go through a high, has to go round. Round the top usually, which is the bulge, and either side of the bulge, where the flow comes back down, you get the 2 dips. The image that gets used, and it's a good one, is a rock in a stream. Water comes down the stream, hits the rock, splits round it, rejoins on the far side. The rock doesn't stop the water. It just decides where the water goes, and it keeps deciding day after day for as long as it sits there. Now the consequences of that. Under the bulge, the top of the omega, the ridge, you get high pressure, sinking air, no cloud, and sunshine. Every day, for as long as it lasts. Either side of it, under the dips, you get low pressure and stagnant grey wet weather that also doesn't move. Which is why omega blocks produce the genuinely strange situation where one part of a country bakes for a fortnight, while a region a few hundred miles away has rain every single day, and neither of them changes. There's a term for the temperature side of this, the upside-down pattern. Places that should be warmer than their neighbours end up colder, because the blocks flipped the geography. It's one of the two things forecasters watch for when a block sets up. That and flooding, because a stalled low-pressure system parked over one catchment for a week is exactly how you fill a river. So, what makes them happen? This is where it gets good, because for most of the history of meteorology, the honest answer was that nobody really knew. Blocking has been described since the 1940s, almost as long as we've known about the jet stream at all, and, small coincidence, some of the earliest thinking on it comes from Tucheng Ye, who studied in Chicago under Rossby, who we've already met. Ye noticed that blocks are more common and last longer when the jet's up at higher latitudes, and he had a theory about why involving the noisiness of the atmosphere. At low latitudes, he argued, the air is too chaotic to hold a pattern in place. The big waves get cancelled out by other waves before they can settle into anything. Higher up, they've got room to persist, but an actual predictive theory of when a block forms and why. That was missing for something like 70 years. Forecasters could see them, could sometimes anticipate them a few days out, and could not tell you what governed them. And then, in 2017, two atmospheric scientists at the University of Chicago, Noboru Nakamura and Claire Huang, published something in Science that I think is one of the loveliest ideas in modern meteorology. They weren't looking for it. They were trying to build a proper set of measurements for blocking so they could analyse it. And one of their new metrics was a term that captured how much the jet meanders. And Nakamura looked at the equation he'd written down and realised it was nearly identical to one that had been devised decades earlier to describe traffic jams, actual cars on actual roads. The insight is that the jet stream has a capacity. A road can carry a certain number of cars per hour, and below that number everything flows, and above it, flow collapses, not gradually but suddenly, into a jam that then sits there and propagates backwards even after the original cause is gone. The jet stream, Nakamura and Huang found, does the same thing. It has a capacity for how much meander it can carry. Exceed it, and the flow jams. And once it's jammed, it stays jammed, for the same mathematical reason your Tuesday morning commute stays jammed 20 minutes after the lorry's been moved. Blocking is a traffic jam in the sky. Same equations. Nobody had noticed because nobody thinks about the M25 while they're doing atmospheric dynamics. I think that's my favourite fact in this entire video, and I've been trying to be fair to the others. 70 years of the best atmospheric physicists in the world staring at a thing they couldn't explain, and the answer was in a completely different discipline, written down by traffic engineers, sitting in the open the whole time. Nobody was hiding it. It just never occurred to anyone to look at a motorway. Nakamura's own line on it was that blocking was notoriously difficult to forecast in large part because there was no compelling theory about when it forms and why, which is a fairly generous way of saying we had a name for it since the 40s and a mechanism for it since 2017, and the events it explains retroactively are enormous. The 2003 European heatwave, California's 2014 drought, the swerve Superstorm Sandy made in 2012 that surprised everybody. That was a block deciding where the storm went. Britain's summer of 1976 was a block. The bitter European winter of 2009 into 2010 was a block. Blocks are not exotic. They're one of the main ways weather gets to be memorable. Right. 2026, May. The 25th, at Kew Gardens in London, the temperature hits 34.8, which breaks the UK's May record, a record that had stood since 1922 at 32.8 by a full 2 degrees. Weather records normally fall by a tenth here, 2/10 there. 2 degrees is not a record being broken. It's a record being ignored. The next day, the same station, 35.1. I remember reading that and having to check I'd understood the year right, because 32.8 in 1922 is one of those numbers that had been sitting there so long it had stopped feeling like a record and started feeling like a fact about the country. 104 years, and then a Sunday afternoon in Kew took it out by 2 degrees, and then came back the following day and did it again, which is just rude. That was the first heat wave. It started on the 22nd of May, and Guernsey, Jersey and Wales all took their hottest May day, and the UK took its highest May minimum temperature too, the overnight number, which people pay less attention to, and which matters more for whether anyone sleeps. That one, I do think, deserves more airtime than it gets. A hot day is an inconvenience. A hot night, night after night, is the thing that actually hurts people, and it never makes the front page because you can't photograph it. The Met Office's own event summary said that given the time of year, spring, not summer, this was one of the UK's most extreme high-temperature events in the observational record. Then June. Records again. Which prompted a note from the Met Office at the time that stopped me. Following May, it would be the first time since 1911 that 2 consecutive months had observed record temperatures. 1911. That's not a modern comparison. That's a comparison to a year when the record itself was young. Amber warnings, then red. Red extreme heat warnings for a record 3rd consecutive day. Then July. The 10th, at a village called Cotton in the Elms in Derbyshire. 35.2. And I'd never heard of the place either, so I looked it up, and it turns out Cotton in the Elms is the furthest point in Britain from the sea. About 70 miles from salt water in any direction, which for an island is genuinely as far as you can get. Which means the hottest spot in the country that day was the one place least able to phone a friend, because the sea is what keeps the rest of us honest. No breeze off the water, nothing to take the edge off, just an inland village slowly turning into an oven. Of all the villages to hold the number, it's the right one. And that's when the Met Office put out the line that this whole video is nominally about. Dr. Amy Doherty, one of their science managers, not only had the UK now recorded a record 8 days with temperatures exceeding 34 degrees, surpassing the previous record held jointly by 1976 and 2020, but it was also the first year in the UK weather record to see temperatures reach 35 degrees or higher in May, June and July. First year in the record, not first year in a decade, or since records were digitised, or in the satellite era. First, and the record is long. Here's a detail that I think is the most underrated thing in this whole video, and it's about what happens after a record. When the Met Office announces a new national record, it goes out as provisional, not confirmed, provisional. And then somebody has to go and check it, physically, before it gets into the books. The verification process involves a site inspection and a check of the equipment used to take the measurement against a network of stations that are deliberately managed to stay stable and consistent over decades. And there are standards, national and international best practice on how a thermometer should be housed, how far it should be from a building, what the ground under it should be, how high off it, what's growing nearby. If the station or the instrument doesn't meet the standard, the provisional figure gets rejected. It doesn't become a record, it just doesn't count. Think about what that means. Somebody drives to Kew Gardens after the fact and stands there with a checklist making sure the screen is the right height and the grass is the right length, because otherwise the number that went round the world isn't allowed to exist. The May 2026 records went through all of that and came back verified. The highest May maximum and minimum for the UK and for Wales, plus a new highest May minimum for Northern Ireland, 15.9 at Killowen on the 28th. I find this reassuring in a way I struggle to articulate. There's a lot of noise about temperature records and whether they're real, and whether the stations are cited badly. And the answer, at least here, is that a specific human being with a clipboard has already had that thought, on your behalf, and gone and looked. I want to be careful about what that means and what it doesn't, and I'll do the full version of the argument in the next module, so I'll keep it short here. It doesn't mean the jet stream snapped. It doesn't mean it's doing something unprecedented in the history of the planet. What it means is that the UK spent an extraordinary amount of this year sitting underneath a ridge, in the top of an omega, under high pressure, with the rock in the stream refusing to move, and that this year's baseline was warm enough that when the block delivered its sunshine, the number at the bottom came out higher than the number has ever come out before. Same mechanism as January, incidentally. Rock in the stream, jet going round. In January, the rock sat over northeastern Europe and shoved the delivery lane south onto us. In June and July, it sat on us, or just north of us, and the delivery lane went somewhere else, and we got the sun instead. Opposite weather, same physics, different rock. Which is either satisfying or annoying depending on your mood, and I've had both. And since we're on the topic of what causes what, that's probably the moment to get into the argument. I've been circling this one all video, so let's do it properly. There's a story about the jet stream that's been on every news channel this year, and it goes like this. The jet is driven by a temperature contrast. Cold pole, warm south. We established that. Now, the Arctic is warming faster than anywhere else on Earth. That's not in dispute at all. That's one of the most solid observations in climate science, and it has a name, Arctic amplification. So if the pole is warming faster than the mid-latitudes, then the contrast between them is shrinking. And if the contrast is the engine, then a smaller contrast means a weaker engine, which means a slower jet. And a slower jet, like a slower river, wanders more. Bigger loops, loopier loops, and bigger, slower loops get stuck more easily, which means blocks, which means heat waves that won't break and storm trains that won't stop. It's beautiful. It's intuitive. It joins up every single thing I've told you in this video into one clean line. It explains January and it explains July with the same sentence. It was proposed in 2012 by Jennifer Francis and Stephen Vavros, and it landed like a bomb, and it has been fought over ever since. Because here's the problem. When people went and checked, the evidence got wobbly. The University of Exeter, and I want to flag this because I've seen Exeter cited this year, as though they're the ones backing the wavy jet story, and it's the opposite. Exeter is where the strongest challenge to it came from. In February 2020, Russell Blackport and James Screen published in Science Advances. They looked at climate models with strong Arctic amplification in them, and they looked at 40 years of actual observations, and their conclusion was blunt. No evidence, from observations or from models, that Arctic amplification causes a wavier mid-latitude circulation. That's not a hedge, that's a flat. And the specific finding underneath it is the bit that really complicates things. Yes, they said, for 2 or 3 decades starting in the mid-1980s, the Arctic warmed fast, the temperature gradient shrank, and the circulation did get wavier. All 3 things happened together. That's the correlation everybody built the theory on. But the trend towards a wavier circulation reversed in recent years, while Arctic amplification carried right on. So over the full multi-decadal record, the waviness trend comes out at roughly nothing. The waves went up, then they came back down. The Arctic kept warming through both, which is precisely what you'd expect if the 2 things were never causally linked in the first place, and precisely not what you'd expect if one drove the other. Their alternative explanation, and it's a proper reversal, is that the causation might run backwards. A wavier jet pushes warm air north into the Arctic, which warms the Arctic. So instead of Arctic warming making the jet wavy, a wavy jet was making the Arctic warm, and we spent a decade with the arrow pointing the wrong way. And then it got worse for the tidy story because in 2025 a paper in AGU Advances went digging further back. Everyone had been studying waviness from 1979 onwards, because that's when the satellite record starts and the data's good. Fine. Except that meant every study was measuring a trend that begins right at the bottom of something. And when they looked at reanalyses going back further, they found that from 1960 to 1980, the polar jet across the northern hemisphere was often wavier than it was at the peak around 2010. Wavier in the 60s and 70s, before Arctic amplification was doing much of anything. So when a headline says the jet stream is doing something nobody alive has ever seen, well, anyone who was watching charts in about 1968 has seen wavier. That's the honest answer, and I'd rather give it to you than not. Now, I don't want to swing too far the other way, because the pile of studies questioning the Francis and Vavros link is a real pile. Barnes in 2013, Screen and Simmons also 2013, Hassanzadeh and others in 2014, Blackport again in 2022 and 2024. And it is also not the same as the whole field agreeing that the jet is fine and nothing's happening. It isn't. It's an argument. It's been an argument for 14 years and it's still going, and papers are still coming out on both sides, and there are perfectly serious people on each of them. What I can tell you is where the evidence is strongest, and it's somewhere slightly different from where the headlines are looking. Double jets. In 2022, a group led by Ify Rousey at the Potsdam Institute, with Kai Kornhuber and others, published in Nature Communications, and their finding is more specific and, I think, more convincing precisely because it's less sweeping. They found the jet over Eurasia tends to occupy one of about 3 states, and one of those states is a double jet. 2 separate branches with strong wind, one over southern Eurasia and one over the north with a gap between them. And here's the key bit. The number of double jet events per year hasn't really changed. They're not happening more often, they're lasting longer. That's it. That's the whole finding. Same frequency, more persistence. And persistence, as we've established repeatedly, is the thing that turns weather into a problem. Why does a double jet matter? Because that gap between the two branches acts as a waveguide. The confined southern branch traps Rossby waves, and trapped waves amplify, and amplified stationary waves are the recipe for a stuck ridge sitting over one place for a fortnight. It links back to something called quasi-resonant amplification, which is a mouthful for the idea that under the right conditions the waves stop travelling and start standing like a note in an organ pipe. And the number they put on it, the increasing persistence of double jets, explains about 30% of Western European heatwave trends. 30%. Not all of it, not none of it. 30. The rest is the baseline, straightforward warming. The dynamics sit on top of the thermodynamics and make it worse in one particular corner of the world, and that last part is the detail I keep chewing on. Rusi's team found this accelerated heatwave trend is unique to Europe compared with other regions of the Northern Hemisphere. Western Europe is a hotspot dynamically, and other places aren't, and the reason is this jet behaviour rather than anything about European emissions or European geography in the obvious sense. Kornhuber's framing was that understanding atmospheric dynamics is how you anticipate future risk and identify hotspots. Rusi's own conclusion was more measured than a headline would like. It needs further research, but double jet streams and their growing persistence are key to understanding current and future heatwave risk over Western Europe. Needs further research. Key to understanding, not proven, settled, done. She also said something that I think is the most quietly alarming sentence in this entire video, and it's not alarming in the way you'd expect. She pointed out that future research needs to work out how well the models capture these relationships, because if they don't capture them, then projections of extreme heat might be too conservative. Too conservative. Not wrong in the exciting direction, wrong in the boring direction, which is worse. Before I land this, I want to explain why the argument is so hard to settle, because I think knowing that makes the disagreement look sensible rather than embarrassing. The observational record is short. That's the whole problem in one sentence. Good global upper air data starts around 1979, when the satellites went up. Before that, you've got reanalyses, model reconstructions stitched together from balloons and ships and whatever else there was, and they get progressively less trustworthy the further back you push. So the entire question of whether the jet has changed is being asked of about 45 years of solid data, about a system whose natural variability happily operates on the scale of decades. That's not enough. It's not close to enough. 45 years of a thing that swings on a 30-year cycle gives you roughly 1.5 swings, and you cannot separate a trend from a swing with 1.5 swings, which is exactly what that 2025 paper was pointing at when it found the 60s and 70s were wavier. Everyone's been measuring from a low point without knowing it was a low point, because they couldn't see far enough back to tell, and you can't run the experiment. There's one atmosphere. You can't take a second Earth, hold the Arctic at 1980 temperatures, run it for 40 years, and compare. So people use models instead, which is why so much of this fight is actually a fight about models. You impose Arctic warming in a simulation, see what the circulation does, and argue about whether the simulation is any good. There's even a term for the awkwardness here, the signal-to-noise paradox, which describes situations in climate science where the models seem to predict reality better than they predict themselves, which is a genuinely strange result and not fully explained. So when Blackport and Screen say there's no evidence and Francis and Vavris say there is, they're not being stubborn. They're both looking at 45 years of a noisy record and a set of imperfect simulations and reaching different conclusions, which is what 45 years of a noisy record is for. So where does that leave us? Here's my honest position, and I'll say it once and then leave it alone. I think the version of this story where a warming Arctic broke the jet stream and that's why your summer was hot is too neat, and the reason it's everywhere is that it's easy to say in one sentence. I think the version where none of the dynamics matter and it's all just baseline warming is also too neat, and there's decent evidence against it, at least for Europe. And I think the actual answer is sitting in the middle, in the double jet work and in the blocking persistence work, and it's less satisfying because it comes with a percentage attached and a caveat about models. But I genuinely rather have the version with the caveat, a field where two groups of extremely competent people publicly disagree for 14 years and keep publishing at each other is not a field in crisis. That's a field working exactly as designed. The alternative, everyone agreeing immediately in 2012, because the story was intuitive, would have been much more worrying and considerably less useful. Anyway, All of this argument runs on data. Enormous amounts of it gathered in a way that stayed more or less unchanged for 90 years, which is the last thing I want to talk about. Twice a day, every day, everywhere, at midnight and midday Greenwich time, 0 and 12 UTC, which is the same instant everywhere on Earth regardless of what the local clock says. Somebody at somewhere between 800 and 1,000 sites around the world walks outside with a balloon and lets it go. I find this unreasonably moving, and I've been trying to work out why. I think it's the synchronization. At the same moment in Antarctica and in Siberia, and on ships in the middle of the Pacific, and on an airfield outside Nottingham, people who will never meet each other are doing the same thing at the same second, and have been, without a meaningful gap since the 1930s. It's not the same operation Oishi ran. His was a pilot balloon. You watched it through a telescope and inferred the wind from where it went. Modern ones carry a radiosonde, which is a small white box on a string underneath, weighing about as much as a phone, containing a thermometer, a humidity sensor, a pressure sensor, a GPS receiver and a radio. It climbs at about 5 meters a second, and as it goes it talks. Temperature, humidity, pressure, position, continuously, all the way up. The wind comes from the GPS. You don't measure the wind directly at all. You track exactly where the box is, moment to moment, and the box is going wherever the air takes it, so the sideways drift is the wind. Same logic as the theodolite, 100 years on, just with the telescope replaced by a constellation of satellites. It goes up for about 2 hours. It gets to somewhere between 20 and 35 kilometers, well into the stratosphere, 3 times higher than an airliner. The balloon starts at a couple of meters across and expands as the pressure drops until it's the size of a small house, and then it bursts, and the whole thing falls back down under a little parachute. And that's it. That's the end of the radiosonde. Nobody goes and gets it. There are a few programs that recover them, but overwhelmingly, they're gone. Millions of small white boxes scattered across the surface of the planet and the bottom of the oceans, each of which did one job for 2 hours and then was abandoned. The consumableness of it is the thing. We spend money, twice a day, in 1,000 places, on an instrument we will never see again, because knowing what the sky's doing at 0 UTC is worth more than the box. Remember that Baltimore-Washington launch in February 2024, the one that found the second strongest upper-level wind in that station's history going back to the mid-20th century. That's the thing I love about it. That wasn't a mission. Nobody scrambled. It was a Saturday evening, and it was 0 UTC, and somebody let go of a balloon because it was time to let go of a balloon, and it happened to fly straight into one of the most extraordinary winds that station has ever recorded. The extraordinary thing was found by the ordinary routine, which is how most extraordinary things get found. Balloons aren't the only source, obviously. Satellites measure temperature and pressure at different altitudes from above, continuously, over the whole planet, including all the enormous parts of it with no people in them. Commercial aircraft carry sensors and report back automatically. Every airliner crossing the Atlantic is quietly taking observations and handing them in, which means the aviation industry is both a customer of the forecast and a supplier of the data behind it. There are buoys, ships, ground stations, all of it pours into the same place. Supercomputers running models that carve the atmosphere into a 3-dimensional grid and step it forward through physics, one small increment at a time, over and over, until they've built the next 10 days. And what do the humans actually watch for once the model's done? 3 things: position, speed, and shape. Position, because that's the delivery lane. Is the jet north of us, or south of us, or straight over the top? That one number does more to determine your week than almost anything else. Speed, because a fast jet means energized systems and quick handovers. But shape is the one that matters most, and it's the one that ties this whole video together. A jet running fast and relatively flat means changeable weather passing through efficiently. 2 nice days, a wet one, 2 nice days. Nobody writes an article about it. Nobody remembers it. It's the weather working. A jet that's slow and deeply looping is the clearest early warning sign anyone has that whatever is currently sitting underneath you, stormy or scorching, it genuinely doesn't matter which, is going to be there considerably longer than you would like. That's it. That's the tell. Not how bad it looks, how wavy it looks. Which brings me to why seasonal forecasting is still so bad, and I want to be fair to forecasters here because they cop a lot of stick for this. 10-day forecasts now are genuinely remarkably good. A 5-day forecast today is about as accurate as a 1-day forecast was in the 1980s. That's one of the great unsung engineering achievements of the last 50 years, and nobody claps for it because the only forecast anyone remembers is the wrong one. But ask when the jet will buckle into a loop, or split into two branches, or get pinned by a block 3 months out, and confidence falls off a cliff. Because you'd need to know Arctic temperatures, and ocean patterns thousands of miles away, and soil moisture, which sounds irrelevant and isn't, because dry soil can't evaporate, and land that can't evaporate just heats up and feeds the ridge above it. And you'd need to know what's happening in the stratosphere above the jet, because the polar vortex up there can reach down and rearrange everything below it. All of those interact. So the honest answer, most of the time, is that confidence stays low until the pattern is a week or two out, and by then it's not a seasonal forecast, it's a forecast. Now. El Niño! I have to do this bit because it's been misattributed all over the place this year and it bothers me. You'll have seen El Niño blamed for January's storms and for the summer's heat. That is not possible, and the timeline is public and unambiguous. In May 2026, NOAA's Climate Prediction Center had the tropical Pacific at ENSO neutral, not El Niño, neutral. Their discussion at the time said the models favoured El Niño forming by the following month, and persisting through the coming winter, with substantial uncertainty about how strong it'd get. The El Niño advisory, just the actual declaration, the point at which they say it's here rather than it's coming, was issued on the 11th of June 2026, June, which is 5 months after the storms and after the May heatwave had already broken a record from 1922. So El Niño didn't do January. It couldn't have. It didn't exist. And it wasn't the cause of the May records either, and it had barely got going for June's. What it is a story about the winter ahead. It's strengthening. It's forecast to keep strengthening through the end of the year, and there's a 97% chance it persists into early spring 2027. There's a real chance, the figure I've seen is around 63%, of it hitting the very strong threshold around the turn of the year. And a strong El Niño does genuinely reorganize the jet stream, particularly over the Pacific, where it tends to shift the whole thing south and drag the American storm track over the southern states, and encourage that split flow, double branch configuration we talked about. But that's a different video, about a different winter, and I'm not going to pretend it explains a January it hadn't started yet for. I've been fairly hard on the coverage this year, and I want to end this module by being fair, because there was one day where the coverage was right, the 16th of March 2026. In a single day, in one country, the United States had a blizzard dumping snow by the feet around the Great Lakes, damaging high winds with tornado threats inside them, marching across the eastern half of the country, with Arctic cold following behind, an unprecedented heat wave taking hold in the southwest, more than 2 feet of rain still falling in Hawaii, drought across more than half the nation, and Nebraska's largest wildfire on record, the Morrill Fire, which ran 70 miles in 12 hours and eventually took 640,000 acres. All of it, the same day. The Associated Press wrote it up, and the phrase the meteorologist gave them was a jet stream gone crazy, colliding with the normal seasonal clash of cold and warm air. About the only thing missing was a hurricane, and that was purely because it was the wrong time of year. The blizzard itself ran from the 13th to the 17th, bottomed out at 944 millibars, dropped 52 inches near Round Lake in Michigan, spawned 56 tornadoes, and did about $1.4 billion of damage. Across 3 separate outbreaks between the 5th and the 16th, the National Weather Service confirmed 177 tornadoes. That was March. Nevada, for its part, had its warmest March on record at every site, and was drier and less snowy than normal on top of it, which is the quiet half of a month like that. Everyone photographs the blizzard and nobody photographs the snowpack that didn't arrive. There's a phrase the forecasters used at the time that I keep coming back to. They said some of what they were seeing on the maps looked more like June or July than mid-March. Not worse than March, wrong-shaped for March. Which is a different complaint and a more interesting one because it's not about magnitude at all. It's about the calendar coming apart, and what I'd say about that day is, nothing about it required anything new. Every single one of those was the shape of the jet, one rope laid across a continent with enough slack in it to put Arctic air over Florida and June air over Arizona at the same moment. I want to go back to the field, not the one in Cornwall, the one in Japan in 1923, with a man and a theodolite and a balloon he's about to lose sight of. Because the thing that stayed with me while I was putting this together is the shape of what happened to Wasaburo Oishi. He found it. He did the work. Nearly 1,300 launches by hand, over 2 years, and then 18 more years of reports on top of that. He knew what he had. And then he spent the rest of his life trying to tell everybody, in a language he'd chosen because he thought it was the fairest way to tell everybody, and it didn't work. Not because anyone stopped him, because nobody was reading. And now we let go of 1,000 of them a day, twice a day, at the same instant, in 1,000 places, and every single one of those observations goes into a machine within minutes and comes back out as a chart that anyone can look at on their phone for free. The exact thing he could not get 500 people to read, we now generate more of before breakfast than he collected in his entire life. And we still can't tell you what it'll do in October. That's not a criticism, by the way. It's genuinely the thing I like most about all of this. We have more information about the jet stream than Oishi could have conceived of. We have satellites and supercomputers and 100 years of argument about it, and we know what it is and how it's made and why it wobbles, and the honest answer to what happens next season is still mostly, we'll know in a fortnight. The atmosphere is not being coy. It's just very large and it does not owe anybody a straight line. So, the jet stream didn't snap. It wandered south in January and sat still in the summer, and both of those are things it has always done. And the fact that the numbers underneath came out at record levels this year is real and worth knowing, and is not the same thing as a river of air breaking in half. I'd rather leave you with the true version, which is that this is an enormously old, enormously ordinary feature of the planet, doing its ordinary thing on a planet that slowly stopped being the one it grew up on. I've got a few other bits I want to do at some point. There's a whole video in the balloon campaign. I barely scratched it. And there's a lot more in there about the girls in the sumo halls and the geologist reading the sand. There's one in the polar vortex, which is a completely different thing that gets confused with this one constantly. And there's probably one in El Niño, once the winter's actually happened and we can look back at it rather than guess. For now, though, that's the lot. The jet stream is doing all of this right now. 6 miles up, roughly overhead, doing about 110, waving gently, deciding what your Thursday looks like. It has no idea we're here. Sleep well.